Hi all. So this is my solution to the practice problem 7. So I'll post this as both a document and as a video for you because we didn't get to go over it in class, and I can also address that in class on Tuesday. So we're going to start with number 1. And in this case, remember with your continuity that you're running through those 4 major questions on our flowchart. So does it have a fraction? No, it does not. Does it have a radical or an ln? Yes, it does. In that case, we're taking what's underneath the square root, which is the x squared minus 1, and we're setting it less than or equal to 0. Now, for square roots, you could, if you wanted to, make it just less than, but I'm okay also if you go less than or equal to, right? We talked about that in class. All right, now because this is a quadratic inequality, I've got to do this a little bit differently. I've got to say, okay, let's take that and set it equal to 0. And I'm going to factor that as x plus 1, x minus 1. You could also add the 1 to the other side and take the square root. Don't forget your plus minus. That gives me 2 solutions, x equals 1 and negative 1. That's going to break up my interval from negative infinity to infinity at 3 places. So I'm going to go from negative infinity to negative 1, negative 1 to 1, and 1 to infinity. So I have kind of 3 sections of my graph. The question is, on which of these 3 sections is it discontinuous? Because remember, this statement here is where it's discontinuous. So if it's less than or equal to 0 on that interval, then it's discontinuous. But if it's greater than 0, if it's positive, then it's continuous on that interval. So we can kind of sort out which intervals it's continuous and which intervals it's discontinuous. So all we're going to do is choose a test point in each one of these intervals and see what happens when we plug it into the inequality. So from negative infinity to negative 1, I'm going to go ahead and plug in negative 3. So if I square negative 3, so again, I'm plugging that into this inequality right here. Plugging negative 3 in for my x, so negative 3 squared is 9. Minus 1 is 8. That is not less than or equal to 0. And therefore, it fails this inequality. And this inequality means discontinuous. So if it's not true, that means that we are actually continuous on this interval. Then I can check my middle interval. Between negative and 1, there's a 0 there. I'm going to plug that one in. If we plug in 0 for the x that's highlighted, that gives us negative 1 on the left. And that is less than or equal to 0, which tells you that it's discontinuous, right? Because that less than or equal tells us where it's discontinuous. Then for the last interval, choose a number. I'm going to go with 2. Plug in 2. 2 squared is 4 minus 1 is 3. 3 is not less than 0, so it fails my inequality. So it's not discontinuous. It's actually continuous here. And so we have, in conclusion, a gap discontinuity on the following interval. So it's discontinuous there in the middle from negative 1 to 1. And again, you can go either way here, but I'm going to say that it's discontinuous when it's or equal to. So I'm going to put my square brackets here to include the or equal to. And that means that it's continuous on the other 2 intervals from negative infinity to negative 1, parenthesis, 1 to infinity, because here we're not including. Okay, so your square brackets either go on the 1 interval up above or on the 2 middle spots down below. Okay, but that's what we're going to go with for our square root. Okay. Next, number 2 is a fraction. So with fractions, that's our first question. Does it have a fraction? If the answer is yes, and this one does, we're going to take the denominator, the x squared minus 4, and set that equal to 0, because we know that when it has zeros in the denominator, then the function doesn't exist. It's undefined there. So let's go ahead and factor or solve here. So you can add to the 4 to the other side, but don't forget when you take your square root that it's a plus minus. Or safer bet is just a factor, x minus 2, x plus 2. That's going to give me x equals 2 and x equals negative 2. So 2 answers here. And then what we want to do in order to classify here, we're going to have to take the limit. So if we let x equals 2, let's consider the first one. The limit as x goes to 2 of your function. So 1 over x squared minus 4 gives you 1 over 0, and that's an asymptote. If it were 0 over 0, it would be a whole. So we have an asymptote at x equals 2. Then we're going to do the same thing with x equals negative 2. So we have the limit as x goes to -2 of 1 over x squared minus 4. And when we plug that -2 in there, squared becomes 4 minus 4. We get 1 over 0. And that's also going to give us a second asymptote at x equals -2. So those are my two discontinuities. And then if I want to talk about where it's continuous, well, it's continuous on the interval, and I only have to skip over -2 and +2. So I'm going to start at negative infinity. I'm going to go to -2, jump over -2 by using two parentheses there, go all the way to 2, break at 2, and then go all the way to infinity. So it is discontinuous where at x equals 2 and -2 because we have asymptotes, and then it's continuous everywhere else. Number 3 gets us into our piecewise functions. Okay, so remember we're checking three things with piecewise functions. First of all, when I look at the two pieces, those are polynomials. Those are continuous everywhere, so no issues there. Then we look at our breaking point, x equals 0. So I'm going to start by looking at the limit as x goes to 0 from the right and the limit as x goes to 0 from the left. Now I'm doing that here because this is splits at 0. So I have a different function on both sides. So I have to look at the one-sided limits. If you have a does not equal, then you can look at it from both sides for that particular piece. All right, so if we're going to be on the right side, that's the bottom function. So that's the limit as x goes to 0 of x, which turns out to be 0. And from the left-hand side, that's the top piece. And when we plug in 0, we get -1. Now, those two do not match. And when that happens, this tells us that there is a jump at your breaking point, which is x equals 0. If we then wanted to say where it's continuous everywhere except the point x equals 0. So it is continuous on the interval from -infinity to 0 and 0 to infinity. So we just kind of jump over the spot at 0. I did not stay inside the box, but you get the idea. All right, on to the last three, and these are the ones we did not get to in class. Okay. So number 4 here. Now, the first thing we always say is take a look at the two pieces, and this one is defined differently than some of our other piecewise functions. So we treat it slightly differently, but the same logic is going to apply. So my two pieces, -7 is fine, but then I've got 2x squared plus x minus 6 at x plus 2. Well, the only point, so that one does contain a fraction, but the only point that would make my denominator 0 would be -2, and that's also my breaking point, okay? So the only point I have to worry about is x equals -2. So now I need to figure out the limit at that point. Now, normally, this does not equal, right? Normally there's a less than and a greater than. So normally we split our limits from the left and from the right. In this case, it's defined on the left and the right with the same function, that fraction. And the only place it's different is at x equals -2. So I can take the limit from both sides as I go to -2 of the 2x squared plus x minus 6 over x plus 2. Okay, because it's defined on both sides the same. Remember, our limits, we don't care what happens when we get to -2. It just so happens it's a different function at that point, but we only care what's happening on to the left and to the right. Okay. Okay, so if we're finding this limit, if we were to plug this in, we get 0 over 0. So we're going to go ahead and factor here. And I'm going to use the fact that one of these has to be x plus 2 to be able to cancel to help me out. That's going to help me with factoring. So the other term should be a 2x minus 3 in order to make that work, right? To get my first term, I'd have to have an x times a 2x. And to get my last term, I'd have to have a -6, so 2 times -3. Now, if you don't have that, a little side note over here, if you have 2x squared plus x minus 6 and you're attempting to factor it, you can always use the box and circle. I think I may or may not have shown this to you. The 2x squared goes in the first box, the -6 in the bottom, and in our magic circle gets those two things multiplied together. So you're thinking about negative 12. So you're thinking about negative 12 in the same way that you think about the last number when you're factoring normally. So I want two factors of negative 12 that add to positive 1. That's going to be a 4 and a 3 if the 4 is positive and the 3 is negative. So I want 4x and negative 3x. And I'm going to put those in the box, other two boxes. And either way, it doesn't really matter because my box is symmetric. Then I'm going to take a look at this and I'm going to factor the box. So I'm going to look at the first row and I'm going to say, what do those two things have in common? So they have a common x, and I'm going to take that out to the side. What's left goes up above, so 2x minus 3. So I'm kind of like playing Battleship here, right? 2x times x gives me the 2x squared in the corresponding box. And then if I take the 2x out of the bottom number, the 4x, then that means a 2 has to go over here. And then I want to just check to make sure 2 times negative 3 does give me the negative 6. Once I've done that, these two are my factors. So 2x minus 3 and x plus 2 are my two factors, and that's exactly what I had here. Once I have it factored, I can go ahead and cancel. And you've got the limit as x goes to negative 2 of 2x minus 3, and that turns out to be negative 7. Okay. So my limit is negative 7. The value at negative 2 is also negative 7 because of that other piece, the bottom part. And those two match. And when that happens in our piecewise functions, we know that it's continuous everywhere. So on negative infinity to infinity, or on R, you could also use that language as well. Okay. So again, key definition for continuity is, does the limit and the value match? In this case, they do, and therefore it's continuous. Number 5, here's a little more of a traditional piecewise function, the way we're used to seeing this one. Okay, and so we want the limit as x goes to 2, because that's my breaking point. The two pieces are polynomials, those are lines, so that's not a problem at all. We want to go from the right and then from the left. Okay, so on the right, we want the top function because that's the greater than 1, so x minus 2. And down here, we want the left-hand side, so that's the negative x plus 2. When you plug in 2, you get 0 to both of these, and these two match. So this tells me that the limit as x goes to 2 of my function is 0. And the question is, does that match the value? So what is f of 2? Well, for f of 2, we go up here to the function and we take a look at where it's or equal to. This one is the or equal to, so I'm plugging the 2 in there. So 2 minus 2 gives me 0, and yes, they do all match. So again, this one is continuous. In fact, this one is actually a special function. This one is the absolute value of x minus 2. So at 2, we have 0 because that's the value and the limit. And to the right, it goes like this. And to the left, we get a slope of negative 2. And so it's the perfect V-shaped of an absolute value function. And then last one, we've got 3 pieces here. All of our pieces are all polynomials, so all continuous, so I'm only worried here about when x equals 2. So we want the limit as x goes to 2 of my function from the right. The limit as x goes to 2 from the left. And the value. The value is right there. It's 5, right? Because it says or equal to. So 5. And we just need the two limits. So from the right, let's see, the right would be greater than, that's the middle piece, the 3x minus 2. Plug in your 2, and you get 6 minus 2 is 4. So I can already see that something's not going to work because I have a 4 and a 5, and those are different. But we do need this last one, the limit as x goes to 2. If we're on the left-hand side, that's the less than piece. That's the top one, negative x squared plus 8. When we plug in 2, 2 squared is 4. 4, negative 4 plus 8 gives me a 4. So these two match. So the limit as x goes to 2 exists. and is equal to 4, but it doesn't match the value. And when that happens, we know that it's a hole. So we get a hole at x equals 2. And then it is continuous everywhere else. So from negative infinity to 2, and from 2 to infinity.